Hello, and welcome to the Chinese remainder theorem video for senior seminar. My name is Kevin, and let's get this going. So here's the overview. We're going to take a look at some pirates' booty, and then we're going to get into the history of the Chinese remainder theorem. We can do a little bit example. Then we are going to revisit pirates' booty, electric boogaloo, and then we're going to finish off with one more example. So here we go with pirates' booty. Once upon a time, a band of 17 pirates plundered a sack of gold from some poor, unsuspecting chaps on the high seas. When they tried to split it evenly between the 17 of them, 3 gold pieces remained. Some say a brawl ensued, some say they just killed a guy. But one pirate was killed, and then the gold was again tried split evenly between them. And this time, 10 pieces remained. Another pirate was killed or sacrificed or whatever. This next time they tried to split the gold evenly, it worked. There was nothing left over. Everyone had an equal share. So the question is, what is the smallest number of coins in the sack? Before we answer that, we're going to go through a little bit of history. The question was first brought about, and we'll see the question later, in the 3rd century in China by Sun Tzu Xuanqing. Not sure about that pronunciation, but in a book called, or a manuscript called Master Sun's Mathematical Manual. In volume 3, problem 26 specifically is the question that we're going to look at later. This question was also tackled by Aryabhata in 6th century India. He came up with what people called an algorithm for solving this. He also was super influential in the Islamic Golden Age. This guy did a lot of stuff, specifically helped with the Chinese remainder theorem for the purposes of this video. He did so much more than that. It was also touched upon in the 7th century in India by Brahmagupta. Sorry if I'm butchering these names. There's a little bit less about him, but he also contributed to what we now know. 13th century Italy, Fibonacci mentioned it in his book Liber Abaci. This book was influential in bringing the Hindu Arabic like number system to the Western world. I think this was they said this was the first book that showed that to the West. And then of course our friend I didn't put, this is supposed to be Gauss, Carl Friedrich Gauss in the 19th century in Germany, was one of the first guys to talk about congruences, which is modular arithmetic, which I think at this point everybody who is going to view this video has seen either in Arousa's proofs or another proofs class or Cisneros' number theory class. So volume 3, problem 6 from the, what was it? Master Sun's Mathematical Manual. There is an unknown number, and it says if we count them by 3s, we have 2 left over. If we count them by 5s, we have 3 left over. If we count them by 7s, we have 2 left over. How many do we have? So I thought, why don't we go ahead and answer that question? So in a modular congruence system, this is what it looks like. It's the same x. All of these are the same x. If you're unfamiliar with mod, basically you divide by this number and then whatever remains goes out here. So this singular x has a remainder of 2 when divided by 3, remainder of 3 when divided by 5, remainder of 2 1 divided by 7. The first thing we have to check for the Chinese remainder theorem to work is that these are coprime. And what we mean by coprime is that the greatest common divisor of them individually or together, so 3 and 5, 3 and 7, 5 and 7, is 1. If they have a larger common divisor, this is not going to work. So there is a formula, but it's kind of long and gross, so I chose not to write it out. Essentially, you take this number. I'm going to highlight some things actually. This number, the 2 here, comes down here and it gets an x1. And then we already know that this number is going to be work with mod 3, so we have to get our mod 5 and our mod 7 in there, and that's where these numbers come from. The same formula is followed. This 3 here comes from here. And this is actually supposed to be an x2. I'm actually going to change that real quick. Okay, so that's now an x2. And this 3 and 7 come from this 3 and this 7. Same here, this 2 is coming from here. And this 3 and this 5 are coming from here. So the reason we do this is because ultimately at the end, we're going to need to have this component be congruent mod 5 and mod 3. So if it's a multiple of both 3 and 5, and all these are integers, we know it's a multiple of both of them. So it will work out. So we take this portion in the red box, tried to color coordinate it. I don't know if this is visible. Red and pink maybe weren't the best choices. This is the red box, and it corresponds to this red text. So technically you're supposed to do this whole bit out here is congruent to this bit here. This is coming from here. But we really can drop the 2 and make it a 1, and it makes it kind of easier. It's generally easier to find something that's congruent to 1 mod whatever rather than a number larger than 1. And so what we look for here is how many times do I have to multiply 35 before it is congruent to 1 mod 3, meaning when I divide by 3, is the remainder 1? So we divide 35 by 3, and that is, we get to 33 remainder 2. So that's not going to work. So we try 35 times 2. Excuse me. That is 70 divided by 3, 69 remainder 1. Okay, perfect. So we're good. So we know x1 is 2. We do that again. This box becomes this pink text. We do the same thing. I've already dropped the 3 here. So there really should be 3x2 21 congruent to 3 mod 5. I went ahead and dropped that because it's just an extra line to write. So x2 times 21 is congruent to mod 5. We have to do no work on that one. 21 is congruent to mod 5. 21 divided by 5 is 4 remainder 1. Perfect. X2 is 1. X3, oh shit. Sorry. I forgot I was going to do x3 real quick. Okay, so I am going to again skip that top line. I'm going to do this in black. So we have x3 times 15 is congruent to 1 mod 7. Well, 15 is already congruent to 1 mod 7. 15 divided by 7 is 2, remainder 1, perfect. X3 is 1. So now we can fill in, let me go back and highlight some things here. So this X1 is here. This X2 is here. And this X3 is here. So we have X equals 2 times 2 times 5 times 7 plus 3 times 1 times 3 times 7 plus 2 times 1 times 3 times 5. 2 times 2 is 4 times 5 is 20 times 7 is 140. Plus 3 times 1 is 1 times 3 is 9 times 7 is 63. Plus 2 times 1 is 2 times 3 is 6 times 3 is 30. Perfect. 140 and 63 is 203. And then plus 30 is 233. We're not done yet. Excuse me. So right now we have X equals 233. That is not the smallest X that we can get. We have to multiply these numbers and use that as our new mod. So 3 times 5 is 15 times 7 is 105. So we come back down here and we say 233 mod 105. 233 divided by 105 is 2 with a remainder of 23. So 233, actually, write this a little bit differently. Let me say 233 is equivalent to 23 mod 105. And that also accounts for all of the numbers. Basically, we can keep adding 105 to 23, and they will all be in the same equivalence class, which really is like a whole nother video. So we're just going to keep it rolling. So now I think that we have enough time to come, or we have enough knowledge to come back to this sweet pirate problem. So similar to how we did before, there's just things being divided and remainders, or a number being divided by different numbers and a remainder being left. So I took the pleasure of writing the congruence system for you. We have X is congruent to 3 mod 17, right? 17 pirates, they split it up the first time, 3 were left. That's where we get this one. Then they killed a guy, and 10 pieces remained right here. And they killed another guy, and nothing remained. So 0 mod 15. And the question asks, what is the smallest number of coins in the sack? Let's find out. First, we want to check that the GCD is 1, because if not, we can't do it. So 17 is prime. The factors of 15 are 3 and 5, 8, 1, 2, 16. So we're good. So the greatest common divisor is 1. So this one has some bigger numbers to it, but it's the same idea. This 3 here is coming from here. This 10 here Actually, I kind of flipped those, but you can see they're color coordinated. Excuse me, man. Still getting over this cough. And this 0 here goes out here. So now we need to find what our x1, x2, and x3 are. These numbers get huge, so I'm not quite going to go through everything. But again, I dropped the 3 and multiplied 16 and 15. So we have x1 times 240 is congruent to 1 mod 17. So we have to check all the multiples of 240, keep dividing by 17 until we get a remainder of 1. And it would probably take a while, but x1 is 9, and 240 times 9 is 2160. 2160 divided by 17 is 127, remainder 1. We don't actually really care about that. This is what we care about. You can do it on your calculator. Check me. I make mistakes too, obviously. And I want to actually kind of color coordinate here. This piece corresponds with the writing in the black. This piece corresponds with the pink writing. And this piece, sorry for cutting off the 16. Excuse me, 1 second. Sorry, I hope that kept the continuity of the recording. My throat was killing me. I needed some water. Anyway, this portion in the red corresponds to the writing down below in red. Here is the pink box. What times 255 equals 1 when divided by 16 times something? So what times 255 is equivalent to 1 mod 16? That what is 15? 15 times 255 is 3825. 3825 divided by 16 is whatever, remainder 1. It's 239, remainder 1. That would take a while. Again, looking for x3 over here. What times 272 is equivalent to 1 mod 15? That is 8. You'll notice I left some stuff out here. You'll see why. Tried to color coordinate here. This 9 is our x1. X1 term, x2 term, x3 term. And then we multiply them up and add them together. Yeah. This is a big number. It equals 6480. 10 times 15 times 17 times 15 is an even bigger number, equal to 38,250. 16 times 17 times 8 times 0 is 0. So there's no third term here. But we are safe because we know that this 15 and this 15 ensure that whatever this number is congruent to 0 mod 15, or that it works in this equation. Add these up and you get 44,730, and the 4080 comes from multiplying 17 times 16 times 15. So this is a number. The sack, remember, we're trying to find how many gold coins, what is the smallest number of gold coins possible in that sack that would fit the riddle that we were given. 44,730 is a number that would work. But to find the smallest, we have to do mod 4080, and we're left with 3930. So the smallest number of gold coins possible in that sack was 3930. Okay, we're going to do just one more example real quick. I'm not going to color code, but I will talk through everything that I am doing. So we know we have 1x. Maybe I will color code. Sorry if it helps. So we know it's going to be 2 times x1 times 4 times 5. This here, this here, this here. That's going to be plus 1, x1, x2, almost made that mistake again, times 3 times 5. Man. Sorry. Throat's really dry. And then we have a plus 3x3 times 3 times 4. So from this part, again, I'm just going to drop the 2's immediately and go x1 times 20 is congruent to 1 mod 3. So we need to see how many times do we have to multiply 20 to get it to be to get it to be congruent to 1 mod 3. So we try 20. 20 divided by 3, 18, remainder 2. That's not going to work. Multiply it by 2. 40. A quick way, if you're dealing with larger numbers, whatever you multiply this number by, you can multiply this number by as well. So to get to here, we multiplied by 2. To get down to here, we multiplied by 2. 2 times 2 is 4. Mod 3. Excuse me. I want to redo that. What I said is true. We know that whatever we multiply to get to here, we multiply this same number by. 2 times 2 is 4. 4 mod 3 is 1. So our x1 is 2. So we'll do this portion in pink just to keep things a little bit different. We don't need to drop anything because this is already a 1. So x2 times 15 is congruent to 1 mod 4. Okay, so we'll look at 15. That is congruent to 3 mod 4. How about 30? We'll check 30. Well, 3 times 2. So what we're really doing here, this 15 is the same as 12 plus 3. This 12 is our 4s. This 3 is our remainder. So when I know 30 is not going to work because 2 times 15 is the same as 2 times 12 plus 3. What's that going to give us over here? We have a 24 plus 6. Again, the 24 is our fours portion that goes out perfectly, and 6 is congruent to 2 mod 4. So this is going to be a 2 mod 4. So that one's not going to work. Now we have to look at 45. Well, 15 times 3 is 45. 3 times 3 is 9. 9 mod 4 is 1. So our x2 is 3. I'm going to do this portion here in red, and that was, again, I'm going to drop this 3 just to make things simpler. So we have x3 times 12 is congruent to 1 mod 5. So we look at 12. 12 is congruent to 2 mod 5. And we look at 24. To get to here, that's multiplied by 2. 2 times 4, 2 times 2. Sorry, I need cough drops. 2 times 2 is 4. Mod 5, that's still just 4. Okay, so we got to look. Again, 12 times 3, 36. 2 times 3 is 6. 6 mod 5 is equivalent to 1 mod 5. So our x3 is 3. Now we can sort of fill this piece in. Just going to go ahead and copy this bit down. And replace our x1. Our x2 and our x3. Man, I'm really sorry about all this coughing. X1 is 2. X2 is 3. X3 is also 3. Here we go. No more coughing. So x equals 2 times 2 is 4. Times 4 is 16. 16 times 5 is 80. 1 times 3. 1 times 3 is 3. Times 3 is 9. Times 5 is 45. 3 times 3 is 9. Times 3 is 27. Times 4 is 108. And 80 plus 45 is 125, plus 108 is 233. But what were our mods 3, 4, and 5? So really we're looking for 233 mod 3 times 4 times 5. What is that? 60. 3 times 4 is 12, times 5 is 60. And 233 is equivalent to 43. Is that right? No, 53. Mod 60. I lied, more coughing. Anyway, I'm hoping now that you have some more clear idea as to what the Chinese remainder theorem is. Also, I forgot to check 3, 4, and 5. GCD is 1. Anyway, hope you have a better idea of what the Chinese remainder theorem is, and if you run across a problem that looks like this, how you can solve it. All right. Good night. Thanks for joining. Have a wonderful evening.